Welcome back. We're now going to continue our investigation into magnetism by the second one in chapter 21. And remember yesterday we stated, and again, this is the key thing for the entire unit on magnetism, is that all magnetic fields, all magnetic forces are caused by moving electric charges. And we're going to start off today by looking at that specifically. In 1819, a guy by the name of Hans Ørsted was the first to discover that if you had a current flowing through the wire, that it would cause nearby compasses to deflect. And so really quick, what he did was he had a wire. And again, he was just kind of playing around the lab one day, and he had a wire that was hooked up to a switch and a resistor or a lamp or whatever came down like this. And nearby, he had a compass. And what he noticed is that when he would close the switch, so when the switch closed, the compass would deflect. It wouldn't be pointing north anymore. It would turn to a new direction. Well, he tried the compass in that one spot, and then he tried it over on this side. And normally when it was open, switch was open, it pointed north. But it was closed, it pointed, oops, I gotta change colors. My fault, let me go back one. There we go. Change colors. It changed. And it deflected. And so what he theorized was that when you have this moving current going through, it would generate a magnetic field. Now remember, we know that if you suspend a bar magnet, that's all a compass is a suspended bar magnet, that it's going to align itself with the external magnetic field. Now normally that's the Earth. And so it aligns itself with the Earth's magnetic field. If you bring another magnet near it, it'll cause it to deflect. And so obviously this thing, before the current was running through, it was not magnetic. But now all of a sudden it is magnetic. And so what he figured out was that if you run a current through a wire, that wire will generate its own magnetic field. And what was kind of neat here is that, and you're going to get an opportunity to play with this in lab, is that my current, and I'll put this in orange, my current's coming out of the positive, going through my resistor, and it's coming down like this, going around like that. But the magnetic field created was circular. And what he discovered was that it's circular and it bent in a certain, and it spun in a certain direction. Now remember, we also said, the last thing we said yesterday in our notes was that magnetic field lines are closed loops. And so he found out that the magnetic field was circular in this case, and actually I did that all backwards. I have my arrows going the wrong direction. I apologize. I have to back that all up. So if you already wrote it in, I apologize. You're gonna have to go back and erase that. It is still circular, but now the magnetic fields, and I'm gonna tell you how I came up with this here in a second, how I realized that I was wrong. Yeah, let me try and close that up a little bit. And again, I'm trying to make this three-dimensional. If you look at this picture right here, it's a much better diagram than what I was able to draw, because this is actually going in three-dimensional. The magnetic field lines created are always perpendicular to the direction of my current flow. Okay, and so since in this case my current's traveling up the wire, my magnetic field lines are never up and never down. They can be toward, they can be into the board, they can be the left, they can be right, they can be out of the board, but they're never up and down. So the magnetic field lines, I'm gonna put this over here. Magnetic field I'm going to put this up here, created. We're actually going to have another word for it other than created here in a second. The created magnetic field is always perpendicular to current flow. That's supposed to be a perpendicular sign. Perpendicular to current flow. Okay. So that's our picture, okay? We're actually going to talk about a right-hand rule to determine the direction of this, okay? And you're going to actually see it. You can actually see the picture of it here with a right-hand rule, and we're going to go over these tomorrow, and I'll have you practice with it. But the basic premise is this. You're going to use your right hand showcasing conventional current. Your thumb is going to point in the direction that the current flows, and then your fingers will curl in the direction of the created magnetic field. So if you look at these pictures, My thumb is pointed up, my fingers curl in the direction that the magnetic field is created or induced. Now, the next thing he did was he looked at it and said, okay, well, this is cool if we have one single wire, but what happens if we have many wires? Okay, I've got to do first a single loop right here. So if I have a single loop of current carrying wire going this direction, if I have my current traveling in this direction, so there's my I, goes up and around. Okay, from Hans's discovery and the picture we just drew, we know that there is a magnetic field, and I'll put it in purple, that is created that is circular. Circular. I'm trying very hard to go 3 dimensions. It's very difficult to do, but you kind of get the idea. Now, if I use my right hand rule, if I go to my previous one, oh, the current was traveling up. My fingers are going to curl in what looks to be kind of a counterclockwise direction. So I'm going to put those arrows here. So I put that here, counterclockwise, like this. If I do the same thing across the top, thumb points, and as I'm looking at it to the left, fingers curl, so it's going to be going away from me at the top and towards me when it's at the bottom of that wire. If I come down, my thumb now points down, so now my fingers are going away from me on the left, towards me on the right, but in everything here, all the magnetic field lines, all mag field lines pointed out inside the loop. So all these magnetic field lines all point the same direction. Well, if we look at this next diagram that I have here, I have a series of wire loops, and that's what's called the solenoid. And in that case, what happens here is now all of these magnetic fields are all lined up the same way. They're all going to add together. And so what we've got here is that our magnetic field created all add together. And I've got a great video diagram to show you in your own notes and not this one, okay, that actually shows us a little bit better. But all these magnetic field lines all point in that direction. We use a second right-hand rule to determine this. Here, our fingers curl in the direction that the current flows, and our thumb points in the direction of the created magnetic field. But we'll practice that and go over that a little bit more tomorrow. Okay? But what a solenoid does is it creates these very close magnetic field lines. They all build together, and this you should actually recognize this. This looks like a bar magnet. The magnetic field created by the solenoid actually looks like a bar magnet. Okay? We can actually create then what's known as an electromagnet, and you probably have made one of these, hopefully somewhere in elementary school. Somebody actually got you to make this diagram. Oops, hang on. This diagram right here. I can't pick a pen. There we go. Okay, where you take a battery and a wire and you wrap it around a nail or something else like that, and when you close it, when you hook it up to the battery, you're able to pick up paper clips. That's known as an electromagnet. What that bar does, that soft iron rod, that nail that you used before, it concentrates and amplifies those magnetic field lines so that those magnetic field lines are closer together. So the soft iron bar is soft iron, okay? A temporary magnet in this case, because we want to be able to turn the magnet on and off, okay? So soft iron is used to be able to turn magnet on and off. And what it does is it concentrates the magnetic field lines. You should remember from yesterday that the closer together the lines are, the stronger the magnetic field is. The stronger our magnet is. And so if you can get those lines really close, then you can have a very powerful magnet. Okay, these are used, excuse me, these are used in junkyards to pick up cars, 2,000, 3,000, 5,000 pounds. These things are extremely powerful. Okay, I have one in here that I'll show you that can actually suspend and hold a 200-pound person if we had the infrastructure for it. We don't, okay? But I will get it out and we'll kind of play around with it if we can, okay? So that's what electromagnet is. Now, we need to be able to describe these magnetic field lines, to be able to describe the strength a little bit better, okay? And so those lines that we drew actually have a special name, and they're called flux lines. The magnetic field, the magnetic field lines are actually called flux lines. If you watch Back to the Future, talk about the flux capacitor, not the same thing. Okay, same word, it doesn't mean the same thing. Okay, and our units, we measure the number of lines in units called Webers. And so if you count up, let's say you have 10 flux lines, you would have 10 Webers. If you have 15 flux lines, you have 15 Webers. Okay, so Webers, sounds kind of funny. You get the idea. But remember, it's not the number of lines that tells you how strong your magnet is. It's the concentration. And so we want to know what's the density, how close those lines are. So we take the number of lines per unit of area. And so we're going to take, in units terms, the number of Webers, number of lines, per meter squared. And so our strength of the magnet is measured in Webers per meters squared. Okay. Now this sounds kind of funny, so we actually give it another name. This is also known as AKA a Tesla with a capital T, named after Nikola Tesla, not the car. Okay, just so we're aware of that. And the symbol, one last thing, the symbol for this is the Greek letter phi, which is an I with a circle in it. Okay? And this gives us our magnetic field strength. How many lines we have in a certain amount of area. What is the density of those lines? Okay? Now, we have spoken that there are permanent magnets, there are temporary magnets, and there are things that cannot be made magnetic. Some materials can be made magnetic, other materials cannot. If they can be magnetic, they get labeled with a name called ferromagnetic materials. Iron is probably the best known, but you can also have cobalt, you can use nickel, and there are some other ones out there that can be used, okay? But if they can be made magnetic, they are what are known as ferromagnetic, and they have a special property because they are able to align their atoms into areas called domains, okay? So if you ever take a bar magnet that has the north and the south, and let's say you break it in half, you snap it, okay? What you're going to get is you're going to get two bar magnets. So you're going to have a south and a north there, okay? Now, if you keep breaking apart, you're always going to get two magnets, okay? This is different than electricity. With electricity, you can have a negative charge. It's the electron. You can have a positive charge. It's the proton. But you can never have a north pole without a south pole, okay? You're always going to come in pairs. It's been theorized the thing goes monopole out there, but we haven't really gone down that road. We haven't found anything like that. Now, the difference between the reason why this happens, okay, if you have an object that can be made magnetic, what's happening is that inside the atoms of that object are all spinning in the same direction, okay? So what you have then, if you think about your atom, you have electrons that are spinning on the outside of your atom. Electrons are moving electric charges. They generate a magnetic field. Okay? Now, in most situations, in most things, okay, those atoms, they all spin, those electrons are all spinning randomly, and so they don't add up. In ferromagnetic materials, they can add up and make little tiny regions called domains. And so if you have a magnet or an object that can be made magnetic, okay, they have little tiny regions. I'm going to draw this out, and there's a better picture down below. But inside here, all of the atoms will point and generate. So everything inside of this, and I'll highlight it, all of the atoms generate a magnetic field that points in that direction. Over here, in this domain, this tiny little region, it has atoms that all point in that direction. All the magnetic field generated points in this direction. And so this is for ferromagnetic materials. Okay? I'll give you a picture of it down here. So if it's non-magnetic, like this, there are no domains. Okay? If they are magnetic materials, they have domains, okay, but they're not lined up. And if it isn't a magnet, then they are all lined up like that. Okay? So we're going to demonstrate this a little bit more tomorrow, investigate, talk about it a little bit more. But for now, let's have a great day. Everybody, see you later. Bye.